after two successful aircraft and even a quadcopter, the GFA Society decided on building something new and innovative as well. So that's how the GFB project was born.
It was an insane project. As a fresher, it excited me. Realistically, it felt impossible. How can a Foamboard Delta wing with such huge wings hold except to where the moment it lifts off the ground, assuming it ever did?
As president, it was interesting to oversee the whole project, but also as an engineering student myself, it was quite interesting to see how the physics around it actually works and how can we actually make Foamboard into such a big plane.
One of the key aspects, or one of the key tools that made the project easier to work on was having a detailed 3D model of the aircraft that was pretty much complete. We were able to use this, use the guide to build the aircraft because it was so detailed.
The GFA project was something quite new and innovative. I thought the fact that we were using a material to build a plane that no one had really considered using before was quite cutting edge, I'd say.
And it was made in a modular way to be able to transport it, so the wings were detachable from the fuselage and the rudder as well. And that's basically how we transported it. So we had a van hired and we managed to fit both wings in the van.
So the idea of the Delta aircraft was actually all about even before the first ever Mark I aircraft flew. So the project received a green light in the summer of 2023 as part of an internship, of which the main goal was to create something new and massive. The engineering of the Delta actually involved both theoretical and practical parts. The theory guided the shape and the part design, while the practical tests were used to actually validate the computer simulations and theoretical assumptions. The trip to Wales in July focused on actually constructing a scaled normal of the Delta aircraft, and although the Delta did not fly successfully, it only was built in 5 days and needed several more days to get some hands-on experience on actually flying it. The structure actually came out really rigid, and the final design actually used most of it. We made several changes from the actual prototype, in which we added the landing gear, we added a tail wheel, and even with these additions, it still was really important to actually build the systems and get to test them practically. And in 5 weeks, the design was finally completed, and although some parts still needed some upgrades throughout the year.
The main constraints of the Delta aircraft were driven by one of them was the CAA open category restriction that limited our weight to 25 kilograms all at mass. It had to be electrically propelled as well, and the dimensions of the components were driven by the internal dimensions of the Luton van that we transported there. Some of the main challenges faced at the beginning of the project were limited access to workspace at the beginning as well. Restricted workspace meant that we couldn't carry out any test builds early on in the project in the first semester. The early test build showed that there were certain redesigns that needed to be made to make the aircraft both structurally strong enough while still be underweight for the CAA restrictions. Some of the issues faced were the fact that the wings needed to be slightly reinforced. This was found out after one of them was built during a build day. The wing joints as well had to be designed from the ground up. The fuselage had to be reinforced while not adding too much weight, and the vertical stabilizer of the aircraft also had to be redesigned because some of the sizing of it was not. It's one of the main changes that added a little bit of complexity to this aircraft from previous generation of GFA aircraft was the fact that previous generations used primarily 2D structures, with the exception of some tubes that were used. Whereas in the Delta aircraft, a lot of the wing components were 3D components, 3D parts, which increased manufacturing time. Due to the complexity of the components and the amount of redesigns that were required, most of the aircraft was built in the final 3 weeks of the project. Before flight testing showed how much of a push it was at the end to get the aircraft built.
At the end of the 2 weeks, we had the wings completed, except for the skin. We had the fuselage complete, the landing gear complete, and the rudder, and so all the control surfaces as well. So everything was mostly complete. It took like 3 or 4 days to fully finish the aircraft. Once everything was assembled and complete, the final step was to check the center of gravity for stability purposes to see if it's actually going to fly well. But when we weighed it, we realized that it is in the right weight, so under 25 kilos, but the center of gravity was too far back. On the one hand, we had to increase the weight in the nose to get the CG further forward, but we also had to decrease the overall weight. The first thing we noticed is that in the tail, there was an extra section that protruded from the back, which was basically unnecessary, so we just sawed it off. The landing gear, which all the calculations were used to get it the right shape and size and everything, it was quite heavy, and we thought we could do with a lighter landing gear if we make it shorter and narrower, but then we also add a horizontal bar to make it the right strength and weight. And we also planned to skin each individual hole of the wing instead of skinning the whole wing with one big sheet of solar span. We decided to fix the rudder in place, and by doing that we were able to remove the servo, which was another couple of $100. That came with the trade-off of having to program the autopilot and the controls in a way that was a bit more complicated maybe. And secondly, we made all those modifications, and at the end of that we weighed it again, and it was the right weight, and the CG was in the right place. And the last step before flying is checking the electronics and to check the controls and the control authority of the spoilers, for example. So when we did that, the issue was that the spoilers were just not moving enough, which suggested that the servos were not strong enough for the control surfaces we had. We kind of took a risky decision and decided to saw them exactly in half to reduce the weight of the surface and be able to use the same servos to control them. So we did that. And then we tried the servos again, and they worked quite well. We had to do several autopilot related calibrations. So then it was finally time to fly. Yeah. First we did a taxi test to check that it can taxi well, and then we had our first flight. And the first flight was quite successful because it managed to land perfectly with no issues. And then we decided to do a second flight. And in the second flight, it seemed like it was flying well, and I was on the ground station looking at the data, and everything was always fine. And the pilot suddenly told us, "Oh, I lost control." The aircraft basically just pitched down and crashed onto the ground, and the propeller had stopped. The damage to the aircraft was quite impressively low. Front nose, where the propeller was, is the first thing to hit the ground, and it obviously broke off. But the landing gear was intact, although it had gone through the fuselage, and the wings were mostly intact, just there were some little holes, but it was probably stronger than it had to be, which is quite good, I would say. After investigating, we realized that the issue was that the ESC, so the engine speed controller, had basically burned out. Because our connections were down in series, they couldn't get the power to the servos, but the autopilot was still being powered and showing that the signals were passing, but physically the servos couldn't actuate. So that was a big learning point for us, because now we know that to avoid that, we should have parallel connections, and we can add just smaller batteries to power the servos. So no matter what happens, the main battery is to the ESC, to anything, even the autopilot, the servos can still actuate. Thinking even further back, we probably should have thought about electronics with more anticipation. Perhaps the components we were using were not suitable, and they hadn't been tested.
So a few of the issues that we encountered as a society and also as kind of a project team were that we had some retention issues with people not showing up to Wednesday workshops. We had a lot of people starting and then not finishing jobs. With a society that is as big as GFA, where you've got some people coming each week and some people not coming every single week, it becomes difficult to track the progress of each part and in turn the progress of the final product. So to tackle this, we kind of engaged with some socials, got people to be more engaged with the kind of social aspect of the society and not just the project itself. Another issue that we faced was access to facilities. So because of some lab restrictions, we weren't allowed into the Georgeberg A8 lab until the second semester of the year. So this caused some delays in terms of how much we could list cut and put together and the amount of space that we had in general to build the plane. And for that we need the appropriate amount of kind of room to work with, especially when we have 15, 20 society members showing up every week and we need to accommodate for those people. We had set out some key deadlines and key timeframes for the plane, but then these had to be pushed back due to those lack of resources. We also struggled a little bit in terms of getting makerspace sessions as well. So the explanation around that would probably need to be kind of revamped this year.
So in terms of the work we've done in outreach, one of our main events was the Easter Build Day. So we got in contact with a local school. It was the Manchester Academy, and in partnership with the Manchester United Foundation, we held a build day right here at the university. So we invited about 25, 30 school children of ages 14 to 16, just to help us do an initial build of our Delta wing design. And yeah, as well as that, we had a presentation in September, sort of to recap the build day that we did in the previous year. So we went back to that school to sort of feedback our progress on the previous year's aircraft. And yeah, we hope to continue this outreach work in the following years. We'd like to get involved with even more schools, spread our message even further, get more people involved.
As the current design lead, one of the things that I realized is that as these aircrafts get bigger and bigger, we need much more efficient ways to transport them. Carrying the parts manually is not a great idea because of the sheer size. Sometimes these parts just don't fit into certain pathways, and it's not even wise to put them at that risk of breaking. We actually faced the issue of breakage in Freshers Fair 2024 when we had to carry the whole aircraft from Georgeberg to engineering building. This was especially because the fuselage was very fragile after the crash in Wales. And realizing you might need to carry the aircraft for outreach events, it just reinforces the need for transportation. I believe that if we are to carry out a second version of the GFD, we can manage the whole project in a much more sorted manner.
Oh my god!